Okay, welcome everyone to final presentations for Quantitative Entrepreneurship. This is a course that Erica Fuchs and I first conceived of about 2 decades ago and started developing ideas for how to put this course together. What this course does is assess the economic viability of new technologies that haven't been commercialized yet. And we do that in 2 parts. Part of the assessment is to figure out what it would cost to produce this technology at scale. So that means like putting a virtual model of a manufacturing facility together and understanding how various factors like yield rates and material costs and labor and energy and such all add up to drive the cost of producing the technology. And the other part is the market, potential market for this technology. And what we do for that is field conjoint surveys or discrete choice surveys where we ask potential customers which product profiles they would prefer among a set of profiles. And then based on their answers, we infer what they value and how much they're willing to trade off one thing for another. We put all that together to try to understand like how likely is it that this technology could become a profitable venture? And what are the things we could do to reduce cost or improve the market to help make it more profitable? This year we have 4 teams. These teams are always sponsored with real sponsors, either from inside or outside CMU. This year we have all internal projects. Sorry, that's not true. We have 3 internal projects and 1 external project from a CMU alum. So the first that we'll hear from is about interlocking metasurfaces. This comes from Ophelia Bowman's lab. One of the things they develop are these little small structures that you can build with 3D printing, that if you make a whole bunch of them, you can make materials mesh together and lock. And you can use that for a bunch of different things. We're going to use it for the applications of shoes where you can flip out the soles. The second team we have is from Clarissa Clifton at Spaceship Earth Renewables, which they're looking at a process that takes in old foam, like from mattresses or such, and puts it through a process that can recycle that foam into a powder that can be used as an additive for a variety of different substances. And the one we're going to look at is using it as an additive for rigid foam panels for insulation, like say in your home. The third is our Carmel Majidi's lab, the soft machines lab. This team is going to look at a soft material that is a thermoelectric. So you can apply electricity to it and it can heat or cool the material. And because it's soft, you can wear it on your skin. It can heat or cool the skin. And that could be used for a variety of purposes. They're going to be looking at things like sore muscles and that sort of thing that you could use as an alternative to a heat pad or an ice patch. And finally, the last project is from Ryan Sullivan's lab. This is a technology for removing PFAS from water. PFAS are persistent chemicals that are building up in our environment, and they're difficult to get rid of. And this is a unique way to get rid of those chemicals, and we're going to look at an application for applying this method to make premium water for people who are particularly health conscious. So the format will be each team will have 10 minutes to present. I will set a timer. The teams know the drill. They'll get a bell when they have 1 minute left. They'll get 2 bells when they're done. And then we will switch to questions and answers, and we'll try to take a first question or 2 from the sponsor, but we'll also open up to other questions from others in the room. And we'll have about 10 minutes or so of questions, and then we'll move on to the next team. There is food outside, and so after the 4 teams are done, I'll go out and we can enjoy some food and beverages. So with that, we can start with team 1.
Good afternoon, everyone. Thank you so much for coming here. Today, we'll be presenting our analysis on interlocking metasurface footwear, which is sponsored by MindLab. And under Professor Ophelia Bowman, we had a wonderful time working with her. This is our team.
Hi, I'm Jerome. I'm John. I'm Benny.
I'm Tanusha, and our other team member, Vivan. First of all, we'll get together on what interlocking metasurface is. So these are arrays of patterned surface features that can be used for adjacent joining of bodies of different materials. They are customizable, they're multifunctional, and they're non-permanent. These can be used as an alternative for traditional joining methods such as welding, bolts, or adhesives. And these have plethora of applications such as in prosthetics, aerospace, construction, but we have decided to concentrate on swappable soles for shoes. As you can see, there are a variety of soles which can just be swapped into your shoes. So instead of buying a number of shoes, you can just swap your soles and get on with your day. To summarize our findings, we found that it would cost $3 per pair of shoe sole to manufacture and integrate it to shoes. We also found that people are willing to pay $25 for the swappability feature. By this, we are able to capture 42% of our stimulated market share with a 20 million in profit. For future work, we recommend that we use injection molding for mass scale production. We recommend licensing this technology to major footwear brands as a go-to-market strategy. And we recommend targeting athletes and active people because they are willing to pay more for this feature.
Next, we're going to talk about the production analysis. So in our beginning stage, there are two plans that we think about it, which is injection molding and additive manufacturing. But at this moment, we're going to only talk about the injection molding. So start with our production process. This is a process that combines both parallel and sequential steps. In step one, there are two machines working at the same time. The first machine is going to produce the inner ILM sole, which is the one you can see on the top, the sole that attached to the upper part of the shoes. The second machine is going to produce the outer ILM sole, which is the one with the swappability features and could change that based on the customer's own preference. The second step is the cleaning step. The laborer will come up and remove the remaining parts on the mold and prepare for the next production routine. So based on this, we use a production cost-based model. This is a model like based on real road, like how to evaluate the cost, but a smaller scale one. And we use like 5 main cost feature, which is material, labor, energy, tooling, and machine cost. So we plot our unit cost curve on the left plot. As you can see that as the production volume increases, the unit cost decreases. And when the production volume reach around 100,000 production volume, the unit cost start to stabilize. And after that, the cost is around $2 to $3 per unit. We also break down the total unit cost, and we found out that the two main contributors to our unit cost is the material cost and the labor cost. So next, we use the tornado plot to visualize how these cost factors that affects our total unit cost. As you can see on the plot, the top two ones, the material consumption and the material price, are the two most sensitivity factor that will influence our unit cost. So based on this result, we recommend that the sponsor to rather improve the mold designing to decrease the material usage or negotiate to different vendors to find the best price for material use.
Next, we take a look at the market to see what customers are willing to pay and see how these features might affect their preferences. So to start off, we looked at we ran a survey that had a variety of different options. We modeled 4 main product attributes. The first one being price, which started off with the usual price that the consumer would pay for their shoe, up to $75 premium. Then the swappability sole feature, starting with no swapping, up to 5 minutes for the swapping capabilities. The activities covered, going from casual only all the way up to casual, athletic, and outdoor options, and then the different color panels that would be included. So we modeled 2 randomized options that would just give the consumer randomized options between the 4 product attributes, and then the fixed choice options that is meant to represent the current shoes in the market that are just your basic shoe with the usual price, no swapping, and just the basic attributes. So from this survey, we got the following data that consumers are more willing to pay for the swapping sole features and the full activity coverage that we offered. So what this means is that in comparison with a shoe, with the basic shoe that has the regular features, the consumers will be willing to pay about $25 more just to be able to swap their soles and add the whole activity coverage. Next, with this data, we created a simulated market scenario to see how consumers will react if these ILM shoes would actually come to market. So we decided to focus on just a Nike scenario while we were only modeling their shoes, mainly because we didn't model brand loyalty in our survey, and because we wanted to focus on a brand that was well-known with a high number of people. So in this scenario, we offered 3 choices. The first is standard Nike shoe, and the Nike ILM shoe, and another option that we call Nike Velcro. That's just like any other types of competitive sole swapping shoes that might be out in the market. And in this scenario, we got that if all 3 of these options were offered to consumers, we would get about a 42.5 share of this simulated market scenario. Now, what this means is that if Nike were to only adopt this technology for 1% of their shoes, we expect to sell by about 500,000 units, giving us a expected revenue of $61 billion. Next, looking at the tornado plot to see how this expected share changes with price changes, activity coverage, and the differences in our activity, in our product attributes. We see that consumers are most sensitive to price, meaning that if there's any changes in the price, our simulated market share is expected to change a lot. And the next 2, the activity coverage and the sole swap speed, and the next 2 most sensitive. And we also determined that the color customization is not really a huge factor for consumers.
All right, so Benny and Jan talked about the production analysis and also the market analysis. So now let's try to put these 2 together to understand how this entire story plays out. So from our market research, we found out that Nike in the US market sells about 120 million units every single year. And let's say we decide to partner with Nike, and assuming the worst case scenario that Nike adopts 1% of their shoes and transforms them from normal shoes to ILM shoes, we get about 1.2 million units. And based on the analysis that Jan just talked about, we're able to capture about 43% of that. That brings us to about around 500 ILM units. And around that range, we're able to charge our customer $40 premium based on a standard shoe, like $40 more from a standard shoe. That sort of brings us to about $20 million in profit, even in our worst case scenario. And that $20 million is basically split between the technology provider and the shoe provider in this case. This is sort of integrating both the production plot and the market analysis plot that we had. Here you can see the production cost going down as the number of units increases. And one way to interpret the market analysis cost is that if we start charging more prices on the y-axis, the volume sold would be less. And here you can see that even with the large scale of production volume and the units sold, we are always remaining profitable. And the gap between the unit cost and the market analysis can show how much licensing we could charge and also how much R&D budget we have to develop this technology while still remaining profitable over the large scale of production volumes that we have. To conclude, additive manufacturing is the way that this technology is being developed right now, but we assume that there might be need to make this technology using other manufacturing processes such as injection molding, which are cheaper. Also, additive manufacturing could be a viable production method for customers who are willing to pay more, but that's something that we couldn't model during our project. And there's a lot of features that like brand royalty and how established market players would react to our consumer in the market. So those are the factors that we might focus our future work on. But immediately what we would like to say is that our sponsors should start a pilot case where we are making around 100 and 200 units every single year, where that does not cost us much and we are also reaching economies of scale. Again, to conclude, there's a lot of work that needs to be done from bringing this ILM technology from market to from the labs to the market. But we believe that there's a lot of potential, and our market analysis and production analysis have shown us that this is a viable technology that people would actually pay for. And we are really excited about this technology, and we are also excited to see how this plays out in the future. Thank you.
Great. And so Ophelia, turns out she's out of the country. So we're recording it for her, but her graduate student, Anusha Kandikar,
yes,
is here to ask questions on her behalf.
yes. Yeah, this is a great presentation. Thank you. I'm Kirsten Sophia Campy. So I'm not super familiar with most of your work, but this is very impressive. If you could go back to page 5, I'd love to talk more about the manufacturing since that's more of what I'm familiar with. So I really appreciate that you're not at the end that islands are typically manufactured with additive manufacturing because that's pretty much the only way they've been made so far. So I'm not familiar with UVA, but when I imagine like a shoe sole, I imagine something pretty squishy. So I have trouble imagining that islands could be made out of that. So I'd love to hear either how you think these could be made with injection molding, if that's something you looked into, or how you think that would affect the marketability. If they had to be 3D printed.
Yeah, so I think with injection molding, you have a lot of material choices. And I think with additive manufacturing also you have that. But we realized that if you wanted to make this at scale with the sole integrated, that'd be really nice. Professor Bowman did send us one of the print analysis where the sole was like around 300 grams and just the ILM on top was just 6 grams. So the reason why we didn't like sort of do like a plot, like an analysis for injection for additive manufacturing was because of that reason, because in this way you could sort of like integrate both the sole and the ILMs on top of it. And again, we didn't look into how you would do this, but again, our analysis is that we should do an R&D to like understand how the mold design would work to integrate this technology.
Okay, great. Thank you for that. And then I was also just wondering, I know like some modular features exist of like shoes where you can swap out heels and things like that. It's like what other kind of modular features are there for shoes?
I think one of them was Velcro that we saw from our market studies. There is one that I think when you go on hikes, you could like have like grippers essentially that makes. So those are the technologies that we sort of looked at, and I think that's what we did in our market share. That all our competitors were like those Nike Velcro ones. So even if they are existing in the market, our analysis showed us that we will still be able to capture 43%.
Okay, great, thank you.
Thanks so much. Other questions from the audience?
I have a question on the mechanical properties of this technology. Because I would imagine things like shear strength would dictate what type of markets you could enter. When I think of athletic shoes, there are different types. Running shoes have a different sole tread than a tennis shoe. Can you comment on what type of properties this adhesion has when you put soles together?
Yes, I think Anusha would be much more familiar with it, but at least from what we understand is that these interlocking surfaces have different designs and they're able to restrict motion in certain directions. So I think you could have a mix of 2 different designs together where you're able to like prevent movement in the X and Y axis and make it rigid. So again, we didn't look into the mechanical properties of those. We did consider you could have different materials that could be beneficial for the consumer. So let's say I want a more squishy shoes, I could make that sole out of a different material. So I think that's what we did consider. We didn't look into much into mechanical properties of this technology at the moment.
My only comment would be that I would think it would dictate what type of market.
Yes. So I think we did run like 2 surveys, one for the general public and one for people who are who play a lot of sports and are more active. And then I think people who are more active, I think our analysis showed that they were willing to pay much more than the numbers that we showed here. So that's also like a potential market that we could look at.
Anusha, do you know, I have a sense that these are built to handle quite a lot of load and shear, but maybe you could comment more.
Yeah, so ILMs are based around the idea that they're highly customizable. So they consist of like a unit cell that could be like designed for a specific purpose. And then they're also patterned over an array that can also be tiled in a way to achieve different like strengths in that sense. So the conventional designs we have don't really deal with shear strength in that way, but that is actually one of the topics we're looking into in our lab. So that is hopefully something that we would be able to achieve. But of course, that depends on like the manufacturing and everything like that.
I had a question. So you mentioned after you did your market analysis to see the addressable market of 20 million in sales per year, and you mentioned that those proceeds would be split between the technology producer and the producer of the shoes. So what do you think would be palatable for Nike in this case, a percentage of split that would be relative to the investment that they would need to make into their production?
That's a pretty good question. We don't know the ranges. I think that's something that we left up for the part, like our sponsors to like figure that out. We just understand that okay, there's $20 million in profit available, and this is a difficult question that you have to have with Nike to like do that. So
Yeah, there's a lot of input into
Yes,
that.
there is,
So
there is.
You got it.
yes, so
Thanks.
Good question and one we wrestle with.
Yes.
Yes.
So do we.
Other questions?
Could you go back to your manufacturing slide? Looking at the rate or the share of costs between, you had one that talked about the material costs and then also, maybe it wasn't material cost, but materials and then injection molding. Yes, here, thank you. So you're looking at the mold cost for the outer ILM. Did you look into mold wear? And I'm assuming the other ILM surface is just not shown here.
yeah, I think we just took a 2 years period where we would like constantly keep checking the mold in our production analysis. So yeah, but I think that number might be a bit higher also because the design of the molds might be very intricate to get the surfaces done. So we had assumed worst case scenario, but I think those numbers might change a lot still.
Because the mold is different, because you have to like pull the ILM out of the mold.
Yes.
Thank you.
What other products do you think this technology ILM could be applied to? Like whenever I think about like Velcro, I think about like why it was invented, right? Like NASA needs something to keep things in place. Now it's used in automobiles, now it's used for like daily fashion and many multiple applications. So where else do you see this technology applicable? And from what you've done this semester, what are the lessons that you can take if you were to put into that product?
All right, I think when we're doing the initial research about Ireland, I think the technology was initially made for like replacing permanent fixtures like poles and rivets. Again, correct me, Anusha, if I'm wrong here. But I think those are the things that you like when you have a rivet, you need to like remove it basically, like you can't replace it. But with ILMs, you could replace it. So prosthetics is one example where you could like have this like swappable prosthetic. Robotics applications, I think there are a lot of robotics application. I know from one of the class that I'm teaching that they were trying to understand different types of foot design feature for quadrupeds, and just to understand, okay, on different terrain, how would you traverse? So you could have like a swappable swappable ILM surface that could go on quadrupeds that could basically vary according to different surfaces. So if you're going on gravel, you'll have a different, like I would say, sole there for quadrupeds. So I think there's a lot of applications. There might be application in construction. I know one of our teams is doing foam boards. So you could have like ILM surfaces on the wall and just snap them on to the wall. So I think those are a lot of applications. But yeah, I think the application for this is like endless and you can figure out a way to like do things.
Okay, thank you very much.
Thank you.
Let's move to team 2.
I just need to go.
You using your own laptop this time? Okay. Yes.
All right. Hello, everyone. We are team 2 with recycled foam powder. We have the pleasure of working with Clarissa and Tesla Materials with their functionalized additive. So I'm Alexander.
Avinash.
Sense.
Maciej.
So Tesla essentially has a technology that has the opportunity to turn something that would be otherwise waste into a high performance additive. So essentially, recycled foam would go into their foam grinder, turn into a powder, and that could have a wide variety of applications, which we're going to focus on foam boards, as Chirag mentioned. So bottom line of our analysis is that the technology is viable in the foam insulation board market at economies of scale, which is 1 million kilograms per year. and a price of 1.22 kilograms, or $1.22 per kilogram. So on the demand side of things, we found that R value, or thermal resistance, as well as noise reduction, were the most important attributes, a lot more than recycled content, but recycled content did find a premium. So at our economies of scale of 1 million kilograms per year, even in our most pessimistic of cases, the price premium was $7.50. So the disparity between the cost of manufacture and price premium presents a very good economic opportunity. So the production process has 3 main stages. So we get the foam chucks from the recycling facility, fret them up to throw into the grinder, and the grinder is heated up, gas is perfused into it, and after that whole process is done, the foam is bagged up.
So to get an estimate of how much it costs to manufacture, we spoke to equipment vendors, recycling facilities, and a lot of people to sort of get a sense of what the annualized cost estimate would be. And we tried to run our analysis based on 3 different CapEx and OpEx, varying scenarios. We have a pessimistic, optimistic, and base scenarios. And what we found, like Oleg said, is that the economies of scale happen at around 1 million kilograms per year. And at that point, it costs anywhere between $1 to $1.80 to produce 1 kilogram of powder. And doing a deeper dive down into the cost breakdown shows us that material costs, raw material sourcing cost, is the primary driver, is the biggest driver, 62% of the cost. Labor is a close second. But what this indicates is that the highest opportunity for cost efficiency for the manufacturer would be to effectively come up with a great strategy for raw material sourcing. That's going to control a lot of the cost. All that's great, but let's look at what Tessera's powder can actually do. Early testing that they've performed has shown that the powder can improve within foam insulation materials the insulation capability, heat thermal insulation, as well as noise reduction capabilities. That's, of course, in addition to what it already does, which is that it's a sustainable material and it has potential cost saving. But how does that translate to the end consumer? To understand that and quantify that a little better, we went into the market to design a survey where we could understand exactly how much value customers place on each of these materials. To run our survey, we hosted it on Sawtooth platform, and we filtered a bunch of potential respondents down to people who knew the insulation market. So people with some home renovation or construction experience. That way our survey is more relevant. This is a quick look of what our introductory page looked like. Don't get lost in all the information. This is all just to say that we wanted to educate our surveyors to make sure they knew exactly what the constraints were and for someone potentially looking to buy a foam board in the market. Putting all that together, this is a quick view of what our survey looked like on Sawtooth. So we had a randomized survey that tried to simulate the Home Depot sort of shopping experience where you would go see different price attributes, different R value attributes, and pick between your options.
So from the data, we converted the results into willingness to pay estimates. The main takeaway here is that customers value performance much more than sustainability alone. For example, as you can see here, adding a 1 R value is worth about 7.57 per kg, while recycled content is only worth about 1.54 per kg. And noise reduction has the strongest value with $18.46 from low to medium and $12.05 from medium to high. This basically suggests that Tessera should position the additive not just as a recycled material, but as a way to improve board performance. So next, we connected the willingness to pay back to market behavior by looking at how those same attributes affect the predicted market share. So the same story is here. The sensitivity analysis shows that the performance-related attributes shift market share much more than recycled content alone. Here's the next question that we want to answer. Is the market large enough for this opportunity to matter, right? So we look into the total rigid foam board market, which is 110 million boards sold annually. And then we translate that to roughly about 379 million kilograms of raw material. This gives us SAM, serviceable addressable market, of approximately 37.9 kilograms per year. And the question we want to answer is, how big is Tessera's opportunity in this pie? what we realized is that Tessera does not need to become a foam board manufacturer, right? We modeled the adoption through existing brands like John Manville, Owens Corning, Henry, Insofoam, and Armax, which means that Tessera share depends on how much we can capture within each brand, and that's how we get the simulated market share. Before we get to the actual number, the question we need to know is how much we can capture within this brand. This depends on how much value we can provide them. And these are the two ways we can provide value to the foam manufacturers, which is through price premium, which means that the manufacturer can price their boards higher because of our additives, or through cost saving, which means that they can reduce their manufacturing costs with better properties.
So let me shift the perspective here a little bit from unit cost that we presented to you before to what's called displacement cost. So basically, manufacturers who produce insulation panels, they pay about $2 to $6 per kilogram of raw materials, and our product replaces 10% of that input, essentially reducing the cost. We modeled 3 cases: pessimistic, with no cost advantage, and based on optimistic, where we generate some savings. And now moving on to demand modeling. In our pessimistic case, we assume 9 million kilograms of the market, partnering with Armax and Insofoam. No performance improvements, only recycled content, and 50% adoption through a trial product line. We compare price premium and displacement cost versus volume to test that viability. In the base case, we introduce half an hour value improvement and medium noise reduction, still with recycled content and 50% adoption. We expand to Henry Company, now increasing our market volume to 15 million kilograms and improving market share through better attributes. In the pessimistic case, in the optimistic case, we assume a full point of R value and high noise reduction, partnering with Jones Mansville and Owens Corning, which are the 2 biggest players in the US, essentially reaching 23 million kilograms market. And what does this all mean? Let's get into sort of the interpretation of these results. Even in the most pessimistic case, where we assume no cost savings, weakest demand, smaller partners, there is still a gap between the price premium. Price premium, what customers are willing to pay, and displacement cost, what it costs manufacturers to implement. That gap represents available profit across the value chain, including us, of course. Finally, when we model annual profit versus price premium, and we see a clear maximum in the range of $8 to $12 per kilogram, which translates to roughly $3.5 per board at retail. And now I'll pass it to Oleg to walk us through limitations and some conclusions.
All right, so unfortunately, our argument does have limitations, like the laboratory scale, scaling up to the factory scale. We don't know exactly what effects that's going to have. The cost modeling doesn't account for many things that are out of the scope of the course. Willingness to pay was done qualitatively, so we need benchmarks for that. So production can scale $1 to $2, very competitive pricing. Customers do value the performance to R value, the sound reduction and such, a lot more sustainability factor, which we need to run a large survey for those type of things. And the key risk is that the benefits must be proven. Further testing is required, and yeah. Thank you
very much. Who is it?
Great job. It's been like really fantastic working with this group over the course of the semester. You should be very proud of the analysis you did here. I just have 2 quick questions. The first one, I know in your final report, part of your assumptions for the PVCM were that the control systems for the temperature and the gas diffusion were excluded. So those are pretty key parts of the technology. So do you have any sense, if I recall correctly, earlier versions of the PVCM did include those things, so do you have any sense of like the orders of magnitude including those items in the process costs would add to the production costs?
I recall vaguely, Mac, correct me if I'm wrong, but like, the problem with auxiliary systems is you have to deal with piping and control valves and stuff, which scales with like size. So it's a little hard to estimate for like a range of attributes, but I think we saw it added about 5% or so to the scale that we're talking about. At 1 million kilograms, the grinder price would be like significantly higher than the auxiliary cost. So 5 to 10% is what I would say, but I'll check on that.
Okay. No, and then my second question is kind of generally, what is the biggest caveat that you left out of your analysis? So like, I'm going to take this from you and then take it a step further. So what should I focus on first?
I think for me at least, the material testing is obviously we've spoken about this, but proving this in the market is like the opportunity is real. There's a lot of revenue to be made out there on this, but actually testing it with a foam board and whatever other applications that I speak about, like flexible foam, whatever it is, that would really prove it, like in talking to foam manufacturers.
Cool. Thank you.
And I didn't mention, but Clarissa took this course, what, 2-3 years ago? I forget.
It was like 3 years ago.
Something like that. Okay, yeah. So Clarissa took this course and came back for more. So thank you. Appreciate you doing that. Other questions?
I think you. Oh, sorry. I think you mentioned that people didn't. In your survey, people didn't value recycled content as highly as R factor. Do you think that's a function of the design of the survey or the people that you were surveying? Do you think that there's like a smaller niche market that might appreciate having recycled content in their installation? Or is there any like legislation that requires recycling some of this stuff?
So we actually found that with our limited survey, I know we said it was 15 validated respondents. 2 of them kind of messed up their zip codes, so we don't know where exactly they were from. But we found that there was a significantly higher willingness to pay for people in more temperate climates. Like California, for example, just more on the West Coast, people were a lot more willing to pay for that recycled content. So there's definitely some variance there, but it evened out at about 1.5.
Does that track with your California experience?
Is it only by recycled?
That's right, yeah, that's right.
Just to follow up on Cooper's question, I think as part of our capstone project, we also work with Roku, and we realized that construction is also a space. Just wanted to like, what are your thoughts on that? And could you like use the exact same survey analysis for construction also, or do you need to run another survey?
You mean construction, like
for construction applications, yes. Like if I take this, I think we discussed for construction application in like cements. So do you think your survey would still be like valid for that cases, or do you need to like find a completely new survey responders for that?
I think we would. I think we would have to do a completely different base because this was our screening questions were very highly restrictive. We really wanted to drill down on people who have like some experience with foam board insulation. Okay. And we got a lot of feedback on our surveys too, but these are people who either they're involved in some capacity in their home construction, but normally it's through a contractor or through like some intermediary. And it's a lot of, they've heard about these, like our value, for instance, and noise reduction is things they've heard about, but it's not like, they're not like extremely familiar with it, which is why we had that introductory slide necessary for them to like understand what's going on. If you were to enter the construction space, I imagine that's like a whole new set of attributes. And then talking about like material stability and then like, yield stress and all of that, which is a whole new. And I would imagine our survey is designed to hear from the end consumer. Like a construction material, you're not ever really getting to the end consumer. Like you'd have to talk to, it's like a B2B setup at that point. So that would be a different setup for sure.
One quick comment. Whenever I think about chemical manufacturing, I always think about safety. I spoke to Clarissa about this, but safety protocols and monitoring what's in the air. So I think of polyurethane film and isocyanates, free isocyanates and vapors, monitoring like that as you scale. Safety features that need to be put in and monitored, and make sure you're in compliance with OSHA and things like that become really important.
Yeah.
So it's just something to be cognizant.
And I think Clarissa mentioned to us pretty early on that because of OSHA requirements, the size of the particle that comes out of the grinder is very important. If it's too small, that's like you're at a risk of like inhalation, and that's bad for everyone on the lane. So there's like a lower limit, I think, on the size that they're targeted.
You can really change your manufacturing costs and scale.
Yeah, absolutely.
Great. And I will make one comment for both the students and the visitors. I thought that the question about niche markets is good, and one that if you take what you've learned about choice modeling and from this class and then go on to more advanced choice modeling, you can start to answer those questions. You probably need more data than 15 respondents to do that, but nevertheless, those things are possible, just not in one semester. So that's really good. Okay, very good. Thank you. All right, let's go to team 3.
I'll have to right after this first one.
Actually, wants on that. He wants to get more. What's being now?
Hello, everyone. This is our team. I'm Dante. This is Nina. That's Sarah, and that's Antonio. And throughout this semester, we had the pleasure to work with Professor Carmel Mujidi on thermoelectric garments, or more specifically, a thermoelectric relief patch. And in these images, we've showcased what we think are largest differentiators for our product in comparison to what's out there in the market today. Namely, you can see it's very thin, flexible, able to conform to the body easily, while having both heating and cooling capabilities.
For our technology, our product is enabled by a stretchable thermoelectric technology. Using the partial effect, the device could actively provide heating or cooling depends on the direction of the current. Precise temperature control could also be accomplished with supporting components like sensors or control electronics. The key useful application is its somehow softness. So it could conform to your skin better than any rigid alternatives currently in the market. This means the technology could provide important features such as flexibility and different size applications that could offer a variety of relief patch designs that be used.
Let's take a look at the base manufacturing process. We start by creating an elastomer film, and this acts as the flexible base of the device. This film is patterned with holes, which we place the bismuth telluride chips in, and these are the active components that allow for heating and cooling. Then we electrically interconnect it and add a thermal interface layer to improve heat transfer efficiency. And then we add our additional sensor electronics for temperature feedback. So when we look at a scaled manufacturing process of around 100,000 units a year, we automate some of those processes. For the elastomer film, we use elastomer casting. For the bismuth telluride chips, we use pick and place automation rather than manually placing them in. And then we use screen printing and also stencil coating to enable more consistent and scalable production at this large scale.
Yeah, so this is the data that we input for our process-based cost module. So we proposed an array of 120 chips for each module. The number of rays is going to be 5, so we can get 20 by 20 centimeters size our patch. We are estimating an annual production volume of 100,000 units, as we mentioned, and with that production volume, we have a unit cost of $17.49 estimated. So as we can see here, the biggest contributor here is going to be the material cost, mostly on step 2 and step 5. Step 2 being the bismuth telluride chips, and in step 5 we have our electronics that are put together to deliver the temperature control. More specifically, the battery, the lithium polymer battery, the pulse width modulation control, and the strap. We did, as we said, the run for 100,000 units, but we reached scale at 22,000 units, where we reached the unit cost of $17.54. We did a pessimistic and optimistic scenario, but in the baseline, that's the price that we reached. We can see here the 4 levers that I mentioned, the 4 biggest contributors in the electronics and the chips, how they affect the unit price, as we might find, for example, a battery that is cheaper but might provide a lower charge duration, or a battery that is more expensive but we could have bigger or be less comfortable, but it would provide a longer time. Same thing with the pulse width modulation control module. If it's more expensive, it might bring a higher temperature control, which we will see it's actually important for the demand side. And the same goes for the bismuth telluride chips and the strap.
So to capture our product performance, viability in the real world, and also approximate potential market share, we created a survey where each survey respondent was given a series of questions, each asking them to choose between 3 potential products. And each of these products had this list of attributes where each attribute would have a certain level picked at random. So for example, price could be anywhere between $20 and $70. Heating function could be anywhere from no heating whatsoever to high heating, that of like a hot tub. Cooling function also had very similar levels. We had relief duration, which consisted of either 20 minutes, 1 hour, or 3 hours. We had our sizing attribute, and then also flexibility, where they would pick between not flexible, something kind of like plastic, something that's somewhat flexible like rubber, something quite flexible like leather, and then something very flexible like cloth.
So here's an example of some of our choice questions. For each of these questions, we had several options that consisted of a combination of different attributes. And based on the respondents' preferences, we were able to capture their preferences for in terms of which attributes they valued the most. And for some of the attributes, we also provided a none option, such as for heating and cooling, to properly reflect real-world scenarios where consumers may not always want all the functionalities. And furthermore, we included 2 attention check questions that allowed us to filter down the respondents from 154 down to 104 high-quality responses.
And with the results of our survey, we were able to approximate willingness to pay for all of our different attributes. And we can see that high heating and high cooling ended up with very high willingness to pay of roughly around $75 in comparison to the baseline of no heating or cooling whatsoever. We also saw that a relief duration of 3 hours resulted in a willingness to pay of roughly $25 in comparison to 20 minutes. And then we also saw that high flexibility had a very large effect on our product's value as well.
So after we ran the simulated market share scenario, we found that as compared to these other 4 products, our new product is taking simulated 40%. And if we can move to the next one, we're going to see that the different attributes that the compared products had. We ran it from this one. It's just a non-electrical powered patch, just microwavable. This is a electric powered heating device, and then these 2 are actually being able to cool down or heat up, but they are smaller and they are not flexible. So that's what we ran, our comparison. We ran it with a $50 price, and the competitors range go from $30 to $130.
We then ran a sensitivity analysis on our potential market share by varying the levels of these attributes. And so, for example, shifting from a high cooling sensation to a medium cooling sensation actually reduces our market share by a considerable amount. But similarly, increasing the relief duration from 20 minutes to 1 hour increases it from 40 to approximately 48%. And price, as you would assume, fluctuates it both positively and negatively around the baseline.
Okay, other than the attributes, price is another direct and controllable levers in our research. Within the demand range, we observed that changing the price from $50 to $90 will decrease the simulated market share from around 3 million to 1.8 million. This data is pretty useful in our following profit analysis. So combining the design, we are able to calculate our each year profit and each year revenue. In the baseline case, price is maximizing at 90% at $90, giving a profit revenue, a profit value of $131 each year, and a revenue of $163 each year. So the price makes sense as consumers we still assume we have a large simulated market share at the price of $90, and our unit cost stays quite flat after mass production, which makes our model really profitable at a larger price other than our first choice. Under pessimistic and optimistic assumptions, profit is still perform the best at $90. Thus, as it's being really stable, we can assume our recommendation being a fairly robust recommendation.
So in conclusion, we reach a unit cost at around $17.5 when we reach scale, which is above 22,000 units. Our simulated market share is around 40% at around 3 million units. And our profit is maximized at $90 per product. And this is at a slightly lower demand, as mentioned earlier. And our key drivers are found to be for cooling and relief duration. Finally, electronics heavily dominated the costs. And based on these results, we came up with 3 areas of recommendations. In terms of design, the relief duration makes the most significant impact. However, this also will increase battery costs as well. In terms of process, scaling production above 22,000 units allows us to reach unit costs of $17, and also through automation processes. And in terms of strategy, we are positioning as a premium pricing product that is competing based on performance rather than price, such as other competitors on the market. And overall, we're a premium high performance product that has high scalability, margins, and also demand. Thank you.
Carmel.
Yeah, so I do have, just reading your report, I had like a bunch of questions. So what I'll do is probably just email these to you. We don't have to get to all of them now. Up to you guys if you even want to respond to those. But just from the presentation, actually go to slide 12. I had a question about the willingness to pay analysis. So this was based on the survey you did. I think you got like 109, surveyed like 150 people, 109 like completed the survey. And this is based on that. But then in slide 14, you have actual prices of actual products that have some of these features as well. I just wanted to know whether there was any kind of correlation, like were the prices of the commercial products, like based on their features, consistent with what was surveyed in terms of people's willingness to pay?
Yeah, so what we did, as Dante mentioned, we had a set of different questions and attributes that we surveyed on. And then based on those attributes, we went to the market and we find this representative products that had and how these different attributes played out for them.
Right. So is there any correlation? Because like there's overlap between the attributes that you talk about in your survey with some of these existing products, right? And so is there a correlation between the prices of what people were willing to pay with what is actually the products are actually sold for in the market?
Yeah, I mean, that's what we simulated in our market share scenario, right? Like we simulated.
Oh, I see. And so that both were factored in the market share, and that's how you establish the market share.
Yeah.
I was kind of also just curious, like a raw comparison, right? Because there's numbers here, right? $50, $75, whatever, you know, and because if you go to slide 14,
the options that we gave.
Right. So, okay. All right. So that's how you establish the, and then for slide 8, so you mentioned like 22,000, that's where you kind of hit scale for production. What was the limiting factor? Was that like, I mean, I know the battery was a big part of the cost, right? You said like $8 of the, it's like almost half the price was like just the battery alone. Is that what dictated this scale, or was it the bismuth telluride, or what was the kind of the limiting factor here? So how did you arrive at this 22,000 units?
Yeah, we ran the whole cost model with everything played in.
Right.
And we found that at that point, we are able to reduce the amount of money that is invested in equipment, right, based on the manufacturing process.
Okay.
So we reduce the amount of money that is introduced by that production process, right, and the parts itself. But even with that volume, the battery is still the biggest contributor.
It's of interest the price, right?
Yeah.
I'm just, I mean, yeah. So,
On the cost.
Yeah, in terms of cost, right? But for it, basically, this is the outcome of some equation that kind of factors all these things.
Yeah.
But I would still think that, you know, there's probably one, in terms of hitting this kind of steady state, right? Like there was probably like, you know, one value in particular, maybe that, you know, was the last to, you know, to stabilize or kind of, not stabilize, but kind of reach this minimum value. I don't know, I was just speculating. But
we just like model this into 100,000 units, but given the process that we commented early in the scaled process, we know that there are maybe other processes that we can also automate when we reach higher volume. But given that they are not so much a contributor to the cost, more so than the actual electronics, that's why we didn't like dive deeper into the actual processes.
Okay. I guess I don't want to capitalize. I mean, I have a long list of questions, so I'll just kind of maybe just ask one last one. The battery size. So the battery that you did select, was that based on your own technical analysis of what you actually thought like the power demand is for these devices, or is that just something based on the journal publication, or what did you guys use for that?
Yeah, we use the journal publication for the electric power, but we landed on I think it's around in the range of 1,000 to 2,000 milliamps per hour. Yeah, got it. And they are lithium polymers, so they are flexible.
Right.
Yeah.
Okay. Great.
Yeah, and maybe I can ask a follow-up on the economies of scale, but the bismuth telluride and the batteries, do those alone have any economies of scale in your model?
We are considering already like a price on doing that volume, right? Like 100,000 units. So that's the price that we're considering in the model.
And so it's really just the equipment, and like, do you know which pieces of equipment are at really low volume, unit costs go up? What's the biggest driver of the cost being high at really low volume?
For the production?
Yeah.
For the process?
The pick and place machine.
Yeah.
Pick and place
That one's
machine.
pretty expensive. But yeah, at high volumes, it kind of goes down to nothing in comparison to the actual material cost.
And so in practice, if you were really doing low volume, you would do it by hand, which is probably how you do it in the lab. So
yeah.
Great. Other questions?
Are you modeling the actual production of the chips, or are you taking the chips as a fixed unit cost for each device that you sell?
No, we are considering buying the actual chips. Yeah, we're not producing them.
Since this is LTA based, it could quickly flip from heating to cooling and back. Do you think that might be another differentiator compared to competing products on the marketplace?
You mean for the speed that they go back?
Yeah, because sometimes for therapeutic purposes, depending on what you're trying to achieve, you want to do cooling and then heating, and then you might want to cycle back and forth, and this device would allow you to do so.
Yeah, so.
So yes, and during our market survey, we do observe similar product that's able to characterize by its quick switching features. But currently on our market survey, we find like most in some cases, or maybe in a lot of cases, like only heating or only cooling is being more common in the use case, or being more common request for our survey replies. So.
Other questions?
I guess it was just a very general question, like how big is the market for wearables like that? Like, is it a big chunk of the economy, like total?
Yes, it's not there, but we estimated the SAM as 7.5 million units sold a year in online.
Other questions? Okay, great. Thank you very much. Okay, and our last team, team 4.
That's you. For now. Yeah. Oh, there it was. Again, or I have a type.
No. All right, hello everyone. My colleagues and I had the pleasure of working with Professor Sullivan and Dennis Doyle on looking at the commercial potential of some of their PFAS neutralization technology. So we're gonna look over similar process-based cost models as the other team, as well as our market analysis. We looked at premium bottled water as our market potential. So we chose premium bottled water mostly so that we could get access to market data and also ask questions to people that knew what they were talking about and people know what they're talking about when they're buying bottled water. We looked at premium bottled water. We added a step, which is the PFAS neutralization. We'll get into the technical aspects of that in a second. And the result was PFAS-free water. The question we wanted to answer was whether consumer willingness to pay was able to justify the cost of our process. Our process model found that at scale, which we'll get into a second, our process model looked at estimated cost to be 6 cents per bottle of 500 milliliters of water, so 12 cents per liter. Our market analysis estimated willingness to pay over $5, so that's a premium over existing premium bottled water. And we found that there was potential market opportunity as there's several brands, including Voss and Aquafina, that are going through current litigation because their products were found to contain PFAS when their marketing material claims to be pure. So how do we model the process? First, the water has to be aerosolized. So it has to be injected into a jet of air. The size of the droplets are important for the photochemistry step. The aerosol is exposed to an array of vacuum ultraviolet lamps. There's 2 frequencies, light frequencies that we're interested in that that drive the photochemistry reaction that neutralizes the PFAS, and then the aerosol is captured. So the water in the air is then recaptured as a liquid. Our model found again that it's about 6 cents per 500 milliliter bottle at scale. Comparing that to the standard cost for marketing and distribution and bottling of a premium bottled water product, so Voss, Liquid Death, or similar products. There's a lot of market data out there and market analytics that's estimated to be between $1 and $1.50, primarily driven by marketing. So our step in the total cost of producing this water or producing a bottle of premium water is only 4%. Our process as modeled is dominated by the cost of energy. So these percentages are all as a percentage of cost. Energy takes up 45% of the total cost in production. Equipment is also significant. And then labor and other inputs are less significant drivers. We'll get into sensitivity testing in a minute. This chart on the left shows the unit cost of 1 liter of water over different production volumes. So you can see, as expected, in low production with full capital costs, you have very high per liter costs. We hit economies of scale around 3 million liters per year as our process is modeled. Anything beyond 3 million liters per year, and our costs remain about 12 cents per liter. One note here is that we built the system to match, we designed the system to match what most bottling plants are. So most water bottling plants run about 3 to 20 million liters per year. Premium brands tend to be less than that because their distribution is different from like a standard plastic bottle of water. Looking at the sensitivity of our cost model to different inputs, as you can see, the price of electricity dominates the sensitivity. We estimated our commercial price of electricity from Pennsylvania costs, which is about 12 cents per kilowatt hour. If you range that from 9 to 15 cents, it changes the price of a liter of the processed water to between 11 and 13 cents. So you can change the price of electricity pretty significantly and not impact the actual unit cost that much. Lamp costs are our primary upfront costs, our primary infrastructure cost. We ranged those from $17 to $29 with our baseline in the middle, and that impacted it less than the price of electricity. And then our discount rate and our compressor life, two other factors in our model, also impact it, but not as dramatically.
Here's what our survey question typically looks like. And in our choice-based conjoint survey, the respondents had to choose between options with different trade-offs. Like the question representing like all three bottled water options, and we have that vary across 4 attributes: the price, filtration method, PFAS rating, and lab verification. So we can say, for example, the option B at the lowest price at $1.29, and with the highest purity, like the no detectable PFAS less than 0.02 parts per trillion, while option A costs like $4.75, it's much more expensive than option B, but the PFAS rating just meets the EPA standard. So all this force the trade-off allows us to estimate how much the people are willing to pay for the purity. And here's the background information part in our survey. Before the previous question, we offered the definition for the filtration methods, what is PFAS, and we offer the regularly for PFAS level. So we acknowledge that this information might a little bit influence the survey results, but as we can see that the information itself is neutral and factual. So here's what the data tells about the consumer's willingness to pay. We can see like the no detectable PFAS, the consumer value is at the $2.48, and the lab test verified at $2.59. Combine all the three attributes with the $5.35. This data shows us like there's a real quantifiable market for the PFAS-free water, and for the premium segment in the market is willing to pay significantly more for it.
Okay, so now we have gone through our production and market analysis. We're gonna combine these two and present you our integrated analysis. So we use the survey data and we created a similar market between these three products, and we capture our simulated profit based on that. So we have our base water at 75 cents, and our water at $2, and our PFAS-free water swing from $2 to $7. And we have, on the right, we have this graph that tells us annual profit as the price per bottle increases. We have 3 cost scenarios. We have our baseline cost at $1.57. That's how much we're gonna our production, marketing, and distribution gonna cost. And we have optimistic, which is $1.06 and 50 cents less than that. And our pessimistic adding $50 more on our baseline model. And our profit is maximized at $5.45 per bottle, which give us around 14 million each year.
Yeah, so for our recommendations, because our biggest uncertainty is the actual consumer behavior in the real world, we recommend starting with a pilot in 5 to 10 premium grocery stores so that you can actually validate our analysis and further refine pricing and messaging around the bottled water. As well as second, for our other recommendation, we recommend starting in a premium grocery store because that's where consumers seem to consumers that purchase premium bottled water seem to value it the highest. So we recommend starting there
emphasizing no detectable PFAS as well as lab verified and pricing it around $5 per bottle. And then lastly, we recommend optimizing reactor design to reduce energy costs, and then finding a good lamp supplier for long-lasting lamps that are energy efficient, as this will help reduce material costs. We do have a couple of lamp suppliers in our report. And then, yeah, just to summarize everything up, we do believe this to be a viable technology. And based on our analysis, at 6 cents per bottle adds to the production costs, while willingness to pay by consumers is about $5 for PFAS-free and lab verification. And while we only modeled the bottled water because that's where we had the most data, we do see other opportunities to expand this into other like wastewater streams or municipal water facilities that might provide more value for PFAS removal. Thank you all for your time. We will now open it to questions.
Ryan.
Yeah, really nice. It doesn't surprise me, but it's still wild how much people are willing to pay for water. Please don't need for bottled water. Most businesses still do tap water. In your on slide 3, the 3 options in your survey, what were you assuming would be the source of the water that you were then sending through the additional VUV treatment?
So we looked at this as an additional cost to already existing premium bottled water suppliers. So this was whatever Voss or equivalent is bringing into their facility, applying the process to that. Yeah.
Okay, cool, great. And then I noticed there were these wiggles in the cost versus volume, and I'm assuming that's due to lamp replacement costs?
Yes, so the lamps, depending on the volume you're running at and the configuration of your facility, lamps are replaced between every 1 and 5 years. The volume here is actually just instituting a new line. So the lines that we designed are modular, just based on how we wanted to model it. Yeah, the design is very changed. Like the design is very much a prototype design, and it would need to be validated. And it could be changed for really any scale you're looking at. But that is the lamp replacement costs. There's quite a big there's quite a lot of uncertainty in when the lamps need to be replaced. There's like an average value from the manufacturer, and then there's a lot of room on either side of that. And so you would generally replace like 1 at a time. Maybe it would be more efficient to replace them all, or cheaper to replace them all at the same time. But the wiggles that you see there are actually just like adding a new line.
Okay.
Yeah.
And on that note, did you get to kind of playing with the dimensions of each reactor?
Yes.
And kind of exploring like what the optimum dimensions might look like?
So we looked at, initially our model just looked at the lab scale that you guys toured us or showed us in the tour. And we scaled that up and we figured out how long that would have to be to process. We were shooting for 1 million liters a year, and it was something like 40 kilometers long, which we decided was probably, and so we wanted to be shorter. And so we played with a couple different designs. We talked with a couple different people that do similar like aerosol flow. And we came up with this UV lamp array where you actually just have this large rectangular box that you flow the aerosol through, and you have a bunch of lamps in there. And so we're targeting the same reaction time, so the same like residence time, I guess, in the reactor for each particle of water. But you can flow. Sorry?
It sounds like higher light flux.
More
lamps, basically.
Yes. Yeah.
Great.
I think this also reduced our overall labor costs because the lamps can be replaced more easily.
Oh, sure. Yeah, that's a consideration when you scale up. Yeah, this is great. To bring it back to the willingness to pay, I think, really where this would be used first, because the bigger needs is like a water utility, municipal. So then it would be interesting. I know this is out of scope for you guys to explore consumers' willingness to pay an elevated water bill, right? But if you consider $5 for half a liter of water versus what we pay per gallon municipal, but people are often very reluctant to pay more on their water bill, but they'll pay $5 for a little bottle of water.
Especially considering the $5 is for the premium market, whereas the municipality has to feed everyone.
Yeah, great point. Yeah.
Not only that, but the municipality is for my shower and my toilet,
Yeah.
not just for my mouth.
Yes,
So.
well, yes, I know they shower with water, yeah.
Great, other questions?
What is the lab verification process and how is that factored into your cost? Is that something the manufacturer does? Is that something they outsource? Is that something they already do?
It's like when we design the survey, we wanna know like how can consumers know this water is PFAS free. So we just know that we cannot just tell them, show them how what the PFAS to tell them to teach them. So we just think we can add a sticker on the bottle water says like this is a PFAS free. And most of the respondents say they're prefer to choose with the sticker one. Yeah.
And we incorporated the lab verification into our process through batch testing. So we have, I can't remember what the exact number is, but after we produce some units, every other, I don't know, millionth unit is sent off for third-party verification.
Yeah.
Joey also looked into like getting on-site machinery for verification, but it was very expensive and very low use. Like we don't use it that often.
Yeah.
And so we decided just to add the cost of sending it out for verification.
Third party more reliable anyways.
Yeah.
It's great.
Good, other questions? Well, so I have another question because I today went to buy a water filter for under my sink. And Aquasana sells the 3-stage. They take out 99.6% of PFAS, presumably. So my question is, no, that's not bottled water. But my question is, this is a process for destroying PFAS as opposed to capturing it and then putting it in the trash. What do you think? I know this wasn't part of your study, but I just wonder, what do you think about like the role of destruction versus capture?
Yeah, so that the consumer is unlikely to care where the PFAS went after, like whether it was destroyed or just taken out of the water they're going to drink. And so kind of the big caveat on our assessment is that it's very cheap to do RO, well, like compared to this technology, it's fairly cheap to do RO filtering. And that, like you're saying, removes the vast majority of the PFAS. One thing, we did see a high willingness to pay for zero PFAS or undetectable PFAS. A second thing is that's why we suggest looking into other value streams such as waste streams, where you could get nicked for, like if you have a waste stream from making pans or something and that waste stream has PFAS in it, rather than capturing it, you might want to actually destroy it. And you can treat that with this water or treat that with this system. The alternative is perhaps if you're a municipality and you don't want to end up with a filter full of PFAS at some point, you could choose to destroy it with this technology. Yeah, but that is a huge caveat on the implementations.
And to add to that, we did measure that attribute of like the filtration method in our demand analysis, and we found that consumers don't care what type of filtration method it is as much as they do the detectable levels in the bottled water market.
Do they care if it's removing other contaminants as well? Or are they very focused on PFAS right now?
We didn't test for other contaminants.
Okay.
I was just wondering, like, what type of information did you use in the survey about like packaging might play a big role, I think. So that's what I'm trying to get at. Like, how did you portray sort of like informing consumer like what is PFAS and like did you consider packaging in that whole survey design?
This is what we introduced before, like the background information part. I think we just introduced like what is the filtration method, because we also use the filtration method, like we use the normally RO filtration system. This is what we research on the market. And we have the RO plus UV neutralization is our technology. And we just introduced what is PFAS. But actually, based on what we research, like the PFAS has a health risk for the people with the bottled water. But we are just to delete this sentence because we don't want like threaten the respondents like, oh, you should be aware of the PFAS. Yeah, we try to avoid this circumstance happen.
Yeah, that would like artificially sort of like scare them and make them more likely to probably buy it.
Yeah.
Which we will do in our marketing.
Don't die, buy this. Yeah. Very good, thank you.
Okay, thank you, everybody. I thought these were like wonderful projects and great teams, great projects this semester. I just wanted to especially thank our sponsors because what makes this class real. It's fun studying the methods, but it's really applying it to a real project that makes it a true learning experience. It's like wrestling with the things that the math and the data can do, and then like kind of where they don't quite get to the real world. And so, and I also hope that this class provides good service that, you know, people who are developing technologies here and who interact with us, you know, get some information out of these. We've had quite a few cases in the past where sponsors have told us that the information that came out of the projects did inform choices that they made about whether to move forward, how to move forward, what kind of path to take. And we've had students hired by, you know, sponsors a bunch of times in the past. So there's clearly some value that we're seeing there. We love keeping this going. So having sponsors is key. That's the other that I wanted to thank was Cindy and the Tech Transfer Office at CTEC, because that's one of the ways that we find sponsors. I mean, I sort of go through my networks as well, but a lot of times when there's technologies being developed here, they'll talk to the Tech Transfer Office about you know, how to identify a market and how to figure out whether it's worth patenting and those kinds of things. And so this is an extra kind of service we can provide, is to like do this type of analysis, spend a semester with student teams who are learning, but get good enough to really come to conclusions by the end and be able to help inform those choices. So thank you, and I want to keep doing this in the coming years. We do have some food and beverage outside. Do you know what we have? What we ended up ordering? It'll be a surprise. It'll be a surprise. So, Julie, do you want to tell us what it is?
Yeah, there's some sliders and standard soda and crudités and dip and
Which will be delightful. So please come grab a bite with us and chat. And I'll ask all the teams, your sponsors do have the reports and the slides. But when they send you questions, like Carmel said that he would send questions and said, I don't even know if you'll answer it. You should answer those questions. So please enjoy the food out in the hall, and we'll all chat with each other a little bit longer. Thanks so much.